Now, what is the goal? The goal is to estimate the unknown parameter theta. For normal data, theta is a vector of mu and sigma. Thus, the goal is to estimate either mu, which is the mean, or sigma, which is the standard deviation, or both. And typically, the main interest is on location, mu. And mu could be, for example, the milk production of a cow, the height of a tree, or you could imagine other examples as well. And furthermore, mu is quite often modeled using several predictors, so x variables, and some elaborate function structure. This is quite typical in practice where you would want to predict something, for example, using x variables to predict y. But such modeling is not considered in this course. We will focus on the unknown parameter mu, which is the location or the mean. And Bayesians consider this mu as unknown but random. And frequentists consider this mu as unknown but fixed. So what is this difference? Consider a coin toss, or imagine a coin toss. A coin consists of two sides, heads and tails. And imagine the person asks, what's the probability that the coin will land tails? A Bayesian would most likely answer that it's 50-50. If the subjective belief of the Bayesian person is that the coin is fair, thus there is no bias, they would most likely say that it's 50-50. Now, a frequentist would also most likely say that it's 50-50 if they believe that the coin is fair. They would imagine that if the person flips the coin a number of times, the frequentist believes that roughly 50% of the time the coin would land tails. Now, imagine that the person flips the coin and puts their hand on top of the coin. So the person flipping the coin can actually see how the coin landed, but you can't see it. The Bayesian can't see it, and the frequentist can't see it. Now, the person flipping the coin asks, what is the probability that the coin is tails now? Remember, the coin has been flipped already. Now, the Bayesian doesn't see the coin. He understands that the coin has been flipped, but since they can't see it, their subjective belief is still that it's 50-50. To them, it's similar. The situation is similar than before the coin flip, or it's 50% chance or probability that the coin has landed tails. Now, the frequentist, to them, this is now different. The frequentist thinks about the situation in such a way that they think that, the coin has landed either tails or heads. So in a way, the question that what is the probability that the coin has landed tails, the question is stupid. To them, they say that if the coin has landed tails, then the probability that it's tails is 100. And if the coin has landed heads, then the probability that the coin has landed tails is 0. It's either or. Of course, neither Bayesian or the frequentist, they don't know how the coin has landed. There was the difference between these two guys, the Bayesian and the frequentist. Now, imagine the person who tossed the coin lifts or shows a coin. Now, the coin landed heads. What is the probability that the coin has landed tails? Both the Bayesian and the frequentist say that it's 0, of course. Let's talk about a popular frequentist approach for parameter estimation called maximum likelihood estimation. Our model f was a function of x given theta, and we were interested in estimating theta. When this model f is regarded as a function of theta, meaning that x is fixed, then this f is called the likelihood function. And we can do that, but whereas the f of x given theta is a probability density function, when this f is regarded as a function of theta, meaning that x is fixed, then it isn't anymore a probability density function. So no probability inference can be drawn from that. And we can construct a rule called the maximum likelihood estimator, which can be denoted as theta tilde equals delta of x, where x is random data. So whatever your data, one can construct a rule that when you plug in your data, meaning that you fix your data, then for that fixed data, you can maximize with respect to theta. And that rule is called the maximum likelihood estimator. Now let's move on to the app and examine some properties of the maximum likelihood estimate. Let's examine the relation of the maximum likelihood estimate MLE to the data. Open the app and move the slider for the data mean and observe what happens to the MLE, or the maximum likelihood estimate of mu. So move this slider here and see what happens to the mu estimate here. If you wish, you can pause the video here to try out the slider yourself. Otherwise, we'll continue. So if I move the slider up to 130, we observe that the MLE for mu changes to 130. If I move the data mean to 70, we observe that the MLE for mu changes to 70. So the data mean always matches the MLE for mu. And furthermore, see what happens to this, the MLE for sigma, if I change the data mean up to 130, it doesn't change. So changing the data mean only changes the mu, and specifically the data mean always matches the MLE for mu. And you can make similar interpretations when moving the slider for the data standard deviation, but as mentioned, we are mostly interested in mu, or the location, so we won't go over that. You can go over that, changing the data standard deviation, and see how that affects the MLE for sigma if you wish. Now, how does changing the data sample size affect the MLE? Again, you can pause the video here to try this out for yourself. Otherwise, we'll continue. Let's move the data sample size up to 50. We see that the MLE for mu doesn't change. Let's change the data sample size way down to 5. Again, the MLE doesn't change. So changing the data sample size does not affect the MLE for mu.